In this video, we're going to give a proof of the binomial theorem, and then we're going to look at Pascal's triangle and see how the rows of Pascal's triangle can give us the binomial coefficients. So I've got the binomial theorem written out in this box here, and it states that if x and y are variables and n is a non-negative integer, then x plus y all to the power of n is equal to the sum from k equals 0 to k equals n of n choose k times x to the power of n minus k times y to the power of k. So to start proving this then, we'll look at this x plus y to the power of n term, and we know that is equal to x plus y times x plus y times x plus y, and so on. We're going to have n lots of that x plus y term multiplied together. And just to make it easy for when we need to refer back to this equation here, we'll call this equation 1. So by using the distributive property repeatedly, we can carry out the expansion of the right hand side of equation 1, and the result is going to be a sum of terms. So for example, if we look at the first two terms multiplied together and use the distributive property, we'd have x times x plus x times y plus y times x plus y times y. So that would give us x squared plus 2xy plus y squared, and then we'd just use the distributive property again. So then we'd have this x squared term times x, and then plus x squared times y, and then plus that 2xy times x, and so on. So we get then that each term is a product of the form x to the power of n minus k times y to the power of k, where we choose y from k of the factors and x from the remaining n minus k factors, and then we multiply these chosen n terms together. So as we choose y from k of the n factors, and there are n choose k ways of doing this, then we obtain the term x to the power of n minus k times y to the k, n choose k times. So basically what we're saying here then is we've got a set of n elements, which is our n factors, and we're going to choose k of them. So if we're choosing k things from a set of n things, then there's n choose k ways of doing that. So that's why we obtain the term x to the power of n minus k times y to the power of k, n choose k times. So therefore then, our coefficient of x to the power of n minus k times y to the power of k is n choose k. And this is true for all k going from 0 to n. So by the addition principle, we have x plus y all to the power of n is equal to our sum going from k equals 0 to k equals n of n choose k times x to the power of n minus k times y to the power of k. So what we're saying then is, for each of our x to the power of n minus k times y to the k terms, we're finding the number of ways we can choose y from 0 of the factors, and then we add that to the number of ways we can choose y from just one of the factors, and then 2 of the factors, all the way up to choosing y from n of the factors. So that then concludes our proof of the binomial theorem. So you can also prove this by mathematical induction, but we've taken a more conceptual argument approach to proving the binomial theorem, and that can be good to see exactly what is going on and why this formula works. So we'll look now at Pascal's triangle and see how we can use that to help us get the binomial coefficients. So the binomial coefficients are just terms in this form here, this n choose k, because this n choose k, well, that was our coefficient of that x to the power of n minus k times y to the power of k term. So therefore, we refer to that as the binomial coefficient. Okay, so we'll take a look now at Pascal's triangle. Looking then at Pascal's triangle, we're going to see that each row of the triangle gives us the binomial coefficients. So let's see how that is going to work. So we're going to start by writing out our binomial coefficients in this pattern here. We're going to start with 0, choose 0. And we go down and to the left, we're going to have 1, choose 0, and then 1, choose 1. And then we're going to have 2, choose 0, and then 2, choose 1, and then 2, choose 2. So just by convention, we're going to name this row here row 0. So this will be row 1 and this will be row 2. And then we're going to start by naming the entries in each row from 0. So for example, that 2 choose 0 term, we're going to call that row 2 entry 0. So that just keeps things nice and simple if we want to find the n choose k term. So that means we just go down to row n and then across to the kth entry. So the next row then, well, we're going to have 3 choose 0, and then 3 choose 1, 3 choose 2, and 3 choose 3. So I'm just going to write out the next 2 rows, so then we'll have 5 rows of our triangle. So we've got 5 rows of our triangle now, and one key thing we can note is that 5 choose 3 term, which I've written in blue, well, that's equal to the sum of those terms in red in the previous row. So that is 5 choose 3 is equal to 4 choose 2 plus 4 choose 3. And that is just a result of Pascal's rule. So I'll just write out Pascal's rule to remind us what it is. So Pascal's rule just states that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So if we look at that 5 choose 3 term then, well, if we go to n minus 1, so it's going to be the previous row, row 4, and the k minus 1 entry, so it's going to be entry 2, so that's our 4 choose 2. Then we just take that term, and we take the next term in that row, which is 4 choose 3, add them together, and we get that 5 choose 3 term. And that's true throughout the triangle. So for example, if we were to take this, say 5 choose 2 term here, well, that's going to be equal to 4 choose 1 plus 4 choose 2. And this 3 choose 2 term, well, that's going to be equal to 2 choose 1 plus 2 choose 2. So that is true throughout the triangle. The next thing worth noting is the fact that n choose 0 is equal to n choose n, which is equal to 1. So if we have n things and we're going to choose 0 of them, well, there's only one way that we're able to do that. And likewise, if we have n things and we want to choose all of them, well, the only thing we can do is to pick all of them. So there's only one way to do that. So this is useful because if we look at the outside of our triangle that slants down to the left here, well, all those terms of the form n choose 0, so they're all going to be equal to 1. And likewise, on the outside of our triangle slanting down and to the right, all these terms of the form n choose n, so they're also all going to be equal to 1. So this means then that each row starts with a 1 and ends with a 1, and our very first term, that 0 choose 0, that is also a 1. So what we've actually constructed then is Pascal's triangle. This is because to construct Pascal's triangle, we start with a 1 in the top row, and then the next row we start and finish with a 1, and then the next row, which we're calling row 2, because remember we start counting from row 0, we're going to start with our 1, and then the next term is going to be equal to the sum of the 2 terms in the previous row that are nearest to it. So that's that 1 plus 1, and we're going to get 2. And then we finish with a 1, and then the third row, we're going to start with a 1, and then the next entry, well, it's going to be the sum of the 2 terms nearest it in the previous row from row 2, so that's that 1 plus 2 is equal to 3. The next term is 2 plus 1, which is equal to 3, and we finish with a 1. And this is exactly the same thing that's going on in this triangle over here. So each row starts and finishes with a 1 because n choose 0 was equal to n choose n, which is equal to 1. And all the other terms are going to be the sum of the two terms nearest it from the previous row. So for example, if we look at this 3 choose 1 term, then that's going to be equal to that 2 choose 0 plus 2 choose 1. And that's just a result of Pascal's rule here. So for example, that 3 choose 1, or n would be equal to 3 and k is equal to 1. So n minus 1 choose k minus 1 means just go one row previous, which would be row 2, and one term in that row previous. So if 3 choose 1 is the first term in that row, then we look at the 0 term in that row, which is at 2 choose 0. Okay, and then that 2 choose 1, well, that's our n minus 1 choose k, and summing those together we get our n choose k, which was 3 choose 1. Okay, so I'll write out the next two rows. So I'll go up to row 5 for our Pascal's triangle on the right over here. So we've got our first 5 rows of Pascal's triangle written out here, and we can see by looking at this triangle that we can easily find the binomial coefficients. So for example, if we want to find what 4 choose 2 is, then we just go to row 4 and the second entry. So remember, we start counting from row 0. So row 4 is going to be this row along here, and that entry that I've just highlighted, well, that's entry number 0, number 1, number 2. So 4 choose 2 is 6, and that means 4 choose 3 is 4, and 6 plus 4 was 10, which is 5 choose 3. So that's true across all the rows. So for example, in row 3, we can see 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, and 3 choose 1 is 1. So this is very useful when we're wanting to expand things of the form x plus y to the power of n. So if we look at an example, so say we had x plus y to the power of 4, or n is equal to 4. So to find our coefficients, well, we're going to have 4 choose 0, 4 choose 1, 4 choose 2, etc. Well, we can just come to the fourth row of Pascal's triangle. So we can see our coefficients then are going to be 1, 4, 6, 4, 1. So that means that x plus y to the power of 4 is equal to 1 times x to the power of 4. So it's just x to the power of 4. So that's because we're thinking of this as choosing none of the y's. Then our next term, our coefficient is 4, so we're going to have 4 times x to the power of 3. So we're choosing x from 3 of the factors, and then y from 1 of the factors. So that's y to the power of 1, which is just y. And then the next term, well, it's going to be 6 times x squared times y squared, and then we get plus 4 times x times y cubed plus y to the power of 4. So using Pascal's triangle to get the binomial coefficients is very convenient, provided n is not too large. If n is, say, 20 or 30 or something like that, well, then it's going to be very inconvenient to write out 20 or 30 rows of Pascal's triangle. But otherwise, it can actually be very useful. So that concludes our video on the binomial theorem proof and Pascal's triangle.